All right, so here is our video on simple harmonic motion. A lot of this is pretty similar to just what we were discussing, what we have discussed in class. It's just the basics of simple harmonic motion. So, what is simple harmonic motion? What are our requirements? Basics of calculating period, restoring force, things like that. All right, so by the time you see this video, we will have already done periods. So let's just quick review. We got a wrecking ball. 200 kilograms is hung from a 20.5 meter tall crane. Center of the ball is 1.7 meters off the ground. How long will it take the ball to go from its release point to hit the building, which is directly under the crane? Okay, so wrecking ball, 200 kilograms, um, held from this crane. So that's not a very noticeable pen. Okay, so we've got our crane here. Right, cranes have like this little crisscross thing. La da da, ba ba ba. Okay, so there's our crane holding this wrecking ball, and like any good wrecking ball, right? Miley Cyrus is sitting on top. Okay, so there's our wrecking ball. How long will it take it to hit its crane from its release point? So we have, right, essentially is the pendulum swinging down until it's directly underneath. How long will it take to hit this release point? Or to go from the release point to being directly underneath the crane. Well, right, I didn't tell you the release point. I didn't tell you where this was, but you don't actually need to know it, right? Because does it matter what the amplitude is on period? No. So we can think about the simple harmonic motion in four pieces, right? We have one, two is swinging up the other side, the third is coming back down to the middle, and fourth is over here. This motion to be from the side and then to come down toward the center to just hit right there, that's going to be a fourth of a period. So we're looking for t over 4. That's what we're looking for is t over 4. Oh, and I should do that as a non-slashy fraction. T over 4. That's what we're looking for. Well, period, right, is 2 pi root, this is a pendulum, so L over G, but we want a fourth of the period. So I'm seeing here pi over 2 times the square root of L over G. So we get this pi over 2 square root L. We have a 20.5 meter tall crane, and the center of the ball is 1.7 meters off the ground. So we have this, that's going to be our length. Here, that's the distance the ball is off the ground, 1.7, and the crane is 20.5. So whatever 20.5 minus 1.7 is, which I was about to do mental math, but I don't want to trust that. 20.5 minus 1.7. Here we go, 18.8. So 18.8 is our length of the string over 10. So then if we just plug this all in, so we get pi over 2, and then that's times the square root of 18.8 divided by 10. So there we go. That's going to be our period over 4, 2.15. 2.15, and this is period, which is in terms of seconds. All right, up next, a 2 kilogram mass is hung on a spring, and it takes 0.7 seconds to complete one period. With what force does the spring pull if it's stretched 0.35 meters? Okay, so this is kind of a little composite problem here. So with what force does the spring pull? We're looking for a force of a spring when it's pulled 0.35 meters, when it's stretched 0.35 meters, right? We know that's equal to kx. Well, 0.35 meters, which means we need k. We need k. But the information that we're given about k is, right, the period from a spring equals 2 pi root m over k. We can use this. We're given the period, 0.7 seconds, and we're given the mass, 2 kilograms. We can use that to find K. Then we can take this K and plug it in over here to find the force. So we have our period is 0.7 seconds equals 2 pi square root of 2 kilograms over K. All right, so this gives me 0.7 divided by 2 pi. And if we square all that, that'll give us 2 over K. So do all this, 0.7 divided by 2, and this is where a lot of people make a lot of calculator errors. You need to do divided by pi. If you do divide by 2 pi, that takes it divided by 2 and then times pi. So be very careful about how you enter that into your calculator. So I get 0.0124, 0.0124 equals 2 over K, which means that K is going to be 2 over 0.0124 mathematically. So here we go, 2 over 0.0124, 161, 161, and this is K, spring constant, newtons per meter. So what we have to do now is we bring this all the way back to our initial equation and plug it in. So if I want the spring force, I have to get all these things, right, equals K times X. And our displacement I'm asking about at 0.35 meters. What is the spring force at that location? So 161 times 0.35, that gets us 56.35 or 56.4 newtons. Okay, so those were two definitely on the slightly more challenging end problems that involve periods. Um, if you need to go back through and rewatch how to calculate those, please do so. But I'm going to keep moving. Here's just a note on periods. And this slide is actually set to be skipped in the slideshow. So if you see that, but yes, I'm still on, I just want to make a quick note. We have this thing called the small angle approximation in math, and that is when we can say sine of theta is, and this should really be approximately equal to theta. It has to be in terms of radians. Has to be in terms of radians for this to be true. But for this, the math to work for the period, and you do not have to know anything about the math for the period. If you're interested, please warn me ahead of time that you're going to come in because I'll have to remind myself of the math. It's fairly complex math. But if you're interested, we can talk through how you get that equation for the period of a pendulum, right? The t equals 2 pi root L over G. This only works when the pendulum is around 20 degrees or less. So it does not really work when you're out that wide over there, because if that's our equilibrium line, this is theta. It only works when theta is 20 degrees or less. So just know that. You don't have to really do anything with that, but that's just as a little side note. Okay, on a graph for simple harmonic motion, I'm asking you here, label on the graph minimum and maximum displacement. Where's the minimum and maximum speed? Where is the direction of acceleration? Min and max restoring force, and then where's the velocity to the right and to the left? Go ahead and pause the video right now. Label these for yourself. Once you have these labeled, go ahead and hit play and keep going. So pause right now. Try this for yourself. Okay, minimum and maximum displacements. All right, that is what we call, that's just this word we call amplitude. Amplitude is maximum displacement. So this is going to be max displacement. So I'll label this delta x max. Same thing down here, right? This is delta x max. It's just negative. We get the same thing up here. Amplitude, all of those. But what about the minimum displacement? That's another thing that I'm asking you for. Well, minimum displacement, that the smallest we can go is right 0. So that's going to be delta x min, which really just means delta x equals 0. And that's going to be at any of these locations. Any of these locations that cross the axis. Okay. Next up, minimum and maximum speed. Okay, well, if we imagine a pendulum, right, if we imagine a pendulum just swinging, hanging down there, when it goes through the bottom, it's moving pretty fast. But what about when it's getting up toward the top? Right, at the top, it has to stop and then turn around. So it stops up here and then turns around, comes over to the other side, and then it stops and then it turns around, which means that on the sides there is velocity of 0. So velocity equals 0 meters per second. Velocity equals 0 meters per second. That's true at any of these places where it turns around. And its maximum speed then, well, that's going to be anywhere it crosses the axis. So velocity maximum. We could also understand that in terms of, well, this is just a displacement time graph. And how do we find velocity from a displacement time graph? Slope. So we're looking for what places does this have the steepest slope? And that's going to be anywhere it crosses through um, that x-axis. Okay, direction of acceleration between right and left. The direction of acceleration, well, if it's over on the right side up here, it's in the positive side, so it's going to be on the right. Well, which way's the force? Which way's the force? The force is aimed back toward equilibrium position. So our force is that way, even if our displacement, so delta x is up, but then our force is always back toward equilibrium. What if delta x is over to the negative? What if we have a negative delta x? Well, our force is back toward the equilibrium position. Remember, we went through this conversation in class that part of simple harmonic motion is that the restoring force is proportional to our displacement. So the greater the displacement, the greater the restoring force. So I'm actually going to do this blue one first. Right there is going to be restoring force maximum. Same with right over here, restoring force maximum. Our maximum restoring force comes at maximum displacement. And then when we look at minimum restoring force, right, that's going to be anywhere where just restoring force equals 0. It'll be absolutely anywhere that the restoring force equals 0. Then remember acceleration, right, F equals ma. So whatever force does, acceleration will do. Just divide by mass. So this is also going to be acceleration maximum, but then anywhere it crosses that x-axis is acceleration minimum. All right, last part is velocity to the right and to the left. Velocity right and left, well, remember this is a displacement time graph. So a positive velocity means a positive slope. Positive velocity means a positive slope. So this is going to be velocity right. And then a negative velocity means a negative slope. All right, we just are arbitrarily calling right positive and left negative. We're just arbitrarily calling those. But if I'm moving to the left, that means I have a negative slope. So I have a negative velocity. Velocity is moving to the left. And then over here, same exact thing. Velocity to the right, v right. And then continue on the same pattern. Velocity left. all that good stuff. Okay, so you have to be able to determine from a graph what each of these values is at any given instant in time. Okay, so I just kind of label it there for you, but we just labeled it all together, so don't worry about that slide. All right, so this is a graph of restoring force. What do you notice? Well, I'm hoping you notice that, right, as displacement increases, the absolute value of restoring force increases. It's just the other way, right? Because if I have a pendulum, let's say my displacement is to the left. So my displacement is to the left. Which direction is my restoring force? To the right. Restoring force is to the right. But instead, if my displacement was, I'm just going to say it's a separate pendulum, displacement's to the right, and so delta x is to the right. The previous one I should say negative delta x, because left is negative. So displacement's to the right, restoring force is to the left. So we have a negative restoring force there. Okay, so this tells us if our displacement is positive, restoring force is negative. Hey, look, that's what we see. Displacement is positive, so we see restoring force is negative. But this also tells us, right in our second one over here, if our displacement is negative, then our restoring force is positive. So if our displacement is negative, then our restoring force is positive. Well, it just kind of makes sense. So there we go. There's a graph of restoring force. All right, calculating restoring force. Springs is pretty straightforward. What is the restoring force on a spring with a spring constant of 235 if a 3.7 kilogram mass has been displaced 0.6 meters? And then what about 0.3 meters of displacement? Okay, well, restoring force on a spring, right, if I have a spring, let's say we get a spring attached to a wall, and then the other side is attached to our little block, and there's our block there. Okay, so our block is, I say, 3.7 kilograms. What is the restoring force with a spring constant of 235? 3.7 kilograms has been displaced by 0.6 meters. Well, if I take this block and I displace it, what's the only force that's bringing it back? Okay, let's say I'm compressed this block. So let's say, okay, equilibrium position is maybe right there. Let's say that's equilibrium position. So that means delta x equals 0 at that point. So if we've compressed this spring, what's the only thing pushing this block back? Well, we've got gravity. Well, my pen might decide to work. Maybe. My pen just maybe decides to work on me. So we've got the spring is compressed. The only thing that are acting on it, we've got gravity, down, normal force, up. To the right, right, to the right we have our spring force, and there's nothing to the left. Because if I don't mention friction, that means we're not going to think about friction. So the restoring force is the spring force. So spring force is our restoring force, which just equals kx. Right, okay, we have 235 newtons per meter times x. We've displaced this by 0.6 meters. Okay, meters on top, meters on bottoms. This gives us 235 times 6. 235 times 6. We get a restoring force of 1,410 newtons. Okay, well, what about 0.3 meters of displacement now? Same exact thing. Go ahead and maybe take a moment, pause the video, try this for yourself. But we can get the same thing. Our force of a spring at that point, 235, right? It's just F equals kx times, instead of 0.6, it's 0.3, which if we plug that in, it should just be half of what it was before, which should be 705 newtons. If I did my mental math Right, let's 235 times 0.3. Oh, I did times 6 instead of times 0.6. I apologize sincerely. This should be 141 newtons, 141. And then instead of 705, this would just be 70.5. Yes, because 235 times 0.3. There we go, 70.5 newtons. All right, there's those. Restoring force for spring, pretty straightforward. All right. And then here's just a recap question. What kind of mathematical relationship exists between displacement and restoring force? Take a moment and pause, think about this. This is one of the 3 requirements that we went over in class. What mathematical relationship exists between displacement and restoring force? It is a direct relationship. Right? It has to be proportional to negative delta x. As we get a larger displacement, restoring force increases. And reverse is true as well. This is the same for pendulum. It's just much easier to calculate for a spring. The pendulum one is much more challenging. If you want to see it, come and talk to me, but it is much more challenging. Okay, so we did go through these in class, but the requirements for simple harmonic motion. And yes, the AP test has a pretty good shot at asking, does this qualify as simple harmonic motion? And then you have to go through the thought of, does it fit all 3 of these requirements to answer? So 1, restoring force directly proportional to displacement. That's what we just talked about. So that means that our restoring force directly proportional to this negative delta x. If that's not true, it is not simple harmonic motion. Okay, number 2, no drag, no friction, which means no damping forces. Nothing is slowing this thing down, so the amplitude does not decrease over time. Number 3, frequency and period do not depend on the amplitude. So that means that if you have a pendulum that you hang there, if this is the straight line, that will behave exactly the same as if you have a pendulum that you bring over there, if that's the straight down line. So that means those 2 pendulums, if they have the same length, will have the same period. That is a requirement for simple harmonic motion. All right. Energy now. So take a moment and try to do this on your own. Label the locations for greatest potential energy and greatest kinetic energy. So pause the video, try to do that. All right. So greatest potential energy, right? That means potential energy of gravity equals mgh. Mgh, well, mass stays the same. G stays the same, so the only thing that changes is h. All right, so we go from down here up to the top, down there to the top. That is our h, which means that at this point and at this point, we'll have potential energy of gravity is at its maximum. Our potential energy of gravity is at its maximum. And then down at the bottom, right, we're at the lowest point. All of that mgh has been turned into 1/2 mv squared. All of that has been turned into 1/2 mv squared, so that's where kinetic energy is at its max, is down at the bottom. So we can get this energy transformation and we can actually say, oh, if we know the height that it's at the side, we can figure out how fast it's moving through the bottom. And it doesn't matter what the mass is because, right, you see this is on both sides of the equation. So we can get this relationship GH equals 1/2 V squared, which should look familiar to you from the energy unit. Or if you want to get velocity square root of 2GH. This should look very familiar to you for the energy unit. Guess what? We get the same equation. All right. How about for spring now? Label the locations of greatest potential energy, greatest kinetic energy. This one's a little weirder because it's not just gravitational and kinetic right now, right? We also have, this is broken into gravitational potential energy, but we also have elastic potential energy. We also have the spring potential energy. So, right up here at A and at E, we have gravitational potential energy is at its max. Down at C, right, that spring is stretched out the most, we have elastic potential energy is at its max. Down in the middle of this, at B and at D, that's the center of this wave, the steepest slopes. That's when it's moving the fastest. So our kinetic energy is at its maximum. But these also have some gravitational potential energy, and there is some elastic potential energy because the string is stretched a little bit to hold the mass in the middle, as opposed to this top value where that'll be our unstretched spring, will be that top value up there. So there's some elastic potential energy in the middle, there's some gravitational potential energy, but that's where the kinetic energy is really at its max, is in the middle. So you have gravitational potential max at top, kinetic energy max in the middle, elastic potential energy max is at the bottom. Okay, pause the video and try to do this, label these points of potential energy for both springs and pendulums on the graph. Okay, right up here, right at the amplitudes, it is not moving. Whether it's a spring, whether it's a pendulum, anything like that. If it's not moving, that means kinetic energy equals 0. And if kinetic energy equals 0, that means that all the energy of the system has to be stored in potential energy in one way, shape, or form. So this is at potential energy max. And that's whether it's gravitational potential or whether it's elastic potential, depends on the situation, right? It depends on whether that's a pendulum or a spring. But we know that at the amplitude, potential energy is at its max. But then in the middle, this is moving at its fastest. So that means kinetic energy is at its max. And if our kinetic energy is at a maximum at any of these locations, there's 5 of them shown on this graph. When kinetic energy is at its max, that means that potential energy has to be at its minimum because of conservation of energy. Right? If kinetic energy goes up, then our stored energy has to go down. Okay. One last couple of things on this work done on a pendulum. So we can plot force and displacement, right? Because this is just forces. It's proportional to negative x. So we can know that this force is proportional to this negative displacement because that's part of simple harmonic motion. So that's why we get a negative slope on this graph here. If this was a spring, right, the slope of this graph would be k. If on a spring, slope would equal k. And truly it would be negative k because it's a negative number. If it's a pendulum, the slope becomes a different kind of a thing. Okay, but I point out here that the ends of these amplitude just end. The ends of these lines, they just end. They don't extend beyond. It's not an arrow. These lines just end because we don't have displacement greater than the amplitude, which is this capital A there. Okay, then what is the net work done from the equilibrium position to the top of the swing? Okay, well, first we have to find the equilibrium position. Well, what does equilibrium position mean, right? It means delta x equals 0. So that's equilibrium position right there. So from equilibrium to the top of the swing, that is our first thing that we need to figure out. So from equilibrium to the top of the swing, well, here's our equilibrium. Top of the swing, that's going to be at its amplitude, and it really does not matter which one you pick because they have the same amplitude on both sides. So all we would do, right, this is a force displacement graph. To find work, We just need the area of a force displacement graph. So work equals FD, which in this case is just the area. So we'd get FR times whatever our amplitude is over 2. Right, base times height over 2. So that's from A. That's our work done. But now I'm asking for B, from equilibrium to one side and then back to equilibrium. Well, so for part B, if we go back to equilibrium, so we start at equilibrium, go to one side, and then we go back to equilibrium, what is our overall displacement in that case? Well, our overall displacement equals 0, right? We end in the same place that we start. So we can no longer look at the graph like this. If we end where we start, displacement is 0, which means, what do we know about work? Work equals 0. Okay. And then last one, part C, for one whole period. What do we know about work for one whole period? Well, let's think about the same thing, right? Displacement over a period, right? The definition of a period is it's back where it started. So displacement equals 0 once again, which means what is the work across an entire period? Well, our work equals 0. Or my pen is giving me fits. Work equals 0. So across one entire period, work equals 0. And all that good stuff. Okay. There are 2 more slides here. They just describe the energy transformations of simple harmonic motion, which we kind of did earlier. Right? We talked about all of these for a pendulum, going from potential energy on one of the sides to kinetic energy at the bottom, and then goes back to potential energy, then back to kinetic energy, back up to potential, all that. Then take a look at our springs here. Right, we start with potential. This one's just gravity, turns into kinetic, and then turns all the way into elastic potential, back to kinetic, then turns into gravitational potential. So we get potential, kinetic, potential, kinetic, potential. That's true of all simple harmonic motion. All right, and that should do it for our little video here. If you have any questions, please do let me know. Otherwise, I'll see you next time in class.